Scott Denning, welcome to Off the Leash Podcast.
Thank you.
I think a good place for us to start is for you to share a bit about your career, so we can kick off the conversation.
Sure. Well, I recently retired from Colorado State University. I'm visiting at Yale. I started out as a geology major when I was an undergrad. Worked very briefly in the oil industry in the 1980s. Lucky for me, the oil industry collapsed in 1986 because the price of oil went down. So I lost my job. Yay. And then I went back to school. And I got a PhD in atmospheric science. And for pretty much my whole career, I have been, I try to understand what happens to the part of the CO2 that doesn't wind up in the air. So half of the CO2 from burning fossil fuels is in the air, and the other half is not. And it has been my life's work to figure out where it went and how it got there and whether it's going to come back and bite us in the butt and if there's anything we can do to make it go away faster. So that's kind of my career. And I was a professor, for 30-some years. I taught almost entirely graduate students. I had a whole bunch of my own advisees, my students who've gone off to do big things. And in kind of mid-career, I got a wonderful 10-year project where I developed education resources for climate change for little kids, for undergrads, for old people, for the public. And it changed my life. I loved it. And I was like, wow, this is really more exciting to me. So I kept doing research and I kept having students. But more and more, I sort of transitioned into this climate change communication and teaching. And so now all I do is teach. So I'm retired from my research career. I don't have to write proposals. I don't have to beg for money. No more annual reports. I just talk to students now. That's my thing.
Awesome. I'm just a little bit curious. What do you do in the oil industry?
Well, I was a geologist. I was a young guy. I went out to oil wells that were being drilled. And you have to keep track of which layer of rock you're in as you drill down, and what whether there's oil and gas in there. And if you do find oil and gas, you got to tell the guys on the drill rig to stop. And then they pull the pipe out and see what they've got. But it's a crap job. It's a right out of college geology degree job. Live in a trailer in the middle of North Dakota in the middle of winter, climbing around on steel oil rigs, collecting little drill cuttings, and not a great job.
I'm sure that's where your interest to get more involved in the research came from.
Kind of. I when I was 23 or whatever, I just needed the money. But then after I lost that job, I went and worked for the National Park Service working on a research project with air pollution that gets into snow in the Rocky Mountains, and then tracking what happens to that pollution as it comes down into streams and lakes and stuff. And that was fascinating. And I started meeting all these atmospheric science professors. And one of them offered me a position to be a graduate student, and I moved into this other field. So, it's kind of like geology in that, in geology, you talk about past climates, and in atmospheric science, you talk about the current climate or maybe the future climate. So it was all related.
Gotcha.
But yeah, it's one of the cool things about academia is that you get to sort of follow your interest wherever it takes you, and that's a wonderful thing.
I'm really interested to dive more into the discussion of climate change with you. I think it's good to pull back and talk more about climate change based level. My context of climate change and just the climate in general growing up over the past 22 years, I just experienced, I guess, some small changes in the way the world has looked to me. I'm not necessarily, I took a class called Natural Disasters here. That's about the only understanding I have.
Too bad you didn't take my class.
I know. What class do you teach?
Climate change.
Oh, you teach a class called Climate Change?
Undergraduate climate change class in Yale College. Yeah.
Oh, wow. Should have took it.
Yeah. Oh, well.
Yeah, but so my understanding has been, I grew up, and I think earlier in life, during a time like November 17th or something that is today, it was probably a bit colder Saturday we played Princeton in a football game, and it was about 60 degrees and sunny in New Jersey. And I was, I'm from New Jersey, and that wasn't a thing, I feel like, when I was 6.
Yeah, I get it. Yeah.
And I'm curious, if you were to explain to a beginner what exactly climate change is and how it operates, how would you describe it?
So first I would start with what is climate?
What is climate?
So climate is the average weather. And why does the Earth have the climate that it does? Heat comes in from the sun, and heat goes back out. And if there's more heat that comes in than goes out, it warms up. And if there's more heat that goes out that comes in, it cools off, right? So this is pretty straightforward. Just like anything else, you put a pot of water on the stove, you put more heat into it than comes out, it's going to warm up. And the Earth works like that too. So normally the heat coming in from the sun is balanced by the heat going out to space. But for climate to change, those two numbers have to be different. The heat coming in and the heat going out are not the same. And that's where we are now. There's more heat coming in from the sun than is getting back out to space. Now, why is that happening? It's happening because the carbon dioxide, this gas in the air, is trapping the heat and keeping it from getting out to space. So the sun is still just as bright as it was when you were a baby, but there's less heat getting out than when you were a baby. Not by much, just by a teeny tiny bit, but that accumulates over time and warms up the world. So the world is slowly warming up because more heat is coming in from the sun than can get back out to space.
Heat's getting trapped, less heat's getting out because of CO2 in the atmosphere.
Right.
That the CO2 in the atmosphere is being created by us.
By burning carbon. So carbon plus oxygen makes CO2, right? So the carbon reacts with, an oxygen molecule. Oxygen molecules are O2, so C plus O2 is CO2. Now I got to do this thing with my hands, and you said there's video, right? So so we're good. So the air is almost all oxygen and nitrogen, these two gases, O2 and N2. So you can imagine them like N2 is just two nitrogens bound together with shared electrons. And the outgoing heat that has to cool the Earth is radiation. It's being radiated out to space. And that radiation is electric and magnetic fields that can grab a hold of those shared electrons. You probably remember electrons of negative charge. There's this magnetic field. It can go back and forth. So you can imagine that the field goes through and the electrons go woo, 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 woo. They don't really make that sound. I totally make that part up. But the woo, woo, woo thing means that some of that outgoing energy has been converted from electromagnetic energy to vibrational energy of the charged particles. It's actually vibrating now. That energy has been absorbed, but then it can be re-emitted when the molecule stops wiggling. So it goes woo, whoa, 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 back to its ground state, and a photon comes out. But because almost all the air is O2 and N2, this getting longer and shorter thing is the only thing they can do. But CO2 is different. Carbon dioxide, there's 3 atoms instead of 2. So I'm a little worried about your headphones, but we got carbon dioxide. So there's 3 atoms.
Okay.
So just like O2 and N2 can absorb that photon and go woo, 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 woo. But wait, there's more. It can also go wee, boo, wee, boo, wee, boo, wee, boo, whip, whip. Each one of these different like wiggly ways absorbs a different wavelength of infrared radiation that's going out. And that's how CO2 is a greenhouse gas, and it traps the outgoing radiation. So unlike the regular air, there's a tiny, tiny amount of the CO2, and it is that one and water vapor, H2O, right? Another, it's got 3 atoms, and it does all these different wiggles. Those 2 gases, water vapor and CO2, absorb most of the IR that's absorbed going out of the Earth.
Okay.
And the H2O doesn't accumulate. You put more water in the air, and it just comes back down as rain. But there is no CO2 rain. So when we burn carbon, coal, oil, gas, we're putting CO2 in the air, and it's just stuck. So more and more and more and more absorption of the heat, and this is why we have global warming.
So I'm going to try my best to explain this to you to make sure I understand it.
Yeah.
So the sun has always been the sun. It's no hotter than it was. It's no colder than it was. And the sun radiates heat to the Earth. Once it gets to the Earth, in order for the overall temperature to be level, the same amount has to go back out.
Exactly right.
The problem that we're having is because we're burning carbon, this heat that's going back out into the space is being trapped.
Correct.
By
carbon
atmosphere.
dioxide. Yes.
Carbon
CO2.
dioxide in the atmosphere that is just trapped.
Yep.
How was that?
That's perfect.
Okay.
Yeah.
Anything I'm missing? I feel like...
Well, that's pretty much the story. I mean, you might wonder, now what? So you've probably experienced air pollution. You grew up in New Jersey. Yeah. There's air pollution there. Yeah. The air pollution is worse on weekdays than it is on the weekend because there's more traffic with rush hour traffic on the weekdays. So where does it go on the weekend? Well, it blows away downwind. But more importantly, the kind of air pollution that makes us sick, it does chemical reactions with the air. It reacts with the oxygen in the air, and it turns into other things. So it's actually sort of burned away in the air. But CO2 doesn't do that. CO2 is chemically inert. It does not have any chemical reaction with the oxygen. It's already oxidized. It's like CO2. That's as oxidized as carbon can get. Mm-hmm. So once you put it up there, it is pretty much going to be there, except that some of it also dissolves into the oceans, and some of it is taken up by plants. Mm-hmm. So the long-term problem that we have with CO2 in the atmosphere, which has been kind of my career, is that photosynthesis, this is the growth of plants, sucks CO2 out. Mm-hmm. But then, as you know, plants die. Everything dies. Every living thing will eventually die, and all of the carbon that was stored in the plant comes back out when that plant rots. Okay. And so the CO2, so the having plants does not just vacuum CO2 out of the atmosphere, unless the growth of those plants is greater than the death of those plants. So you can't really expect the plants to bail us out of this, nor the oceans, because the oceans, when you dissolve CO2 in seawater, it changes the chemistry of the seawater, and the seawater can only take up so much. Mm-hmm. So half of it winds up in the air, a quarter of it winds up in the plants, and a quarter of it winds up in the ocean. If you think of the whole pie is the amount of carbon that we burn every year. Half of that pie goes into the air. The other half that doesn't go into the air, half of that goes into the oceans, half of that goes into the plants. But we're kind of stuck with the half that's in the air. It's going to be there for a long, long time.
Can you take me back? Let's say maybe, 200 some years.
Right.
What would you say has been the biggest change to the Earth's climate because of this extra carbon now in the air?
Well, the world is warmer than it was 200 years ago. There's half again as much CO2 in the air as there was 200 years ago. So 50% increase in CO2. On the average, at the surface, the world is 3-4 degrees warmer Fahrenheit than it was 200 years ago. So 200 years ago, Thomas Jefferson, Napoleon, right? This is quite a long time ago, long before I was born. I'm old, but I'm not that old. And because the air is warmer, it can evaporate more water out of the oceans, which means there's more precipitation, more rainfall and snowfall than there used to be. It's changing the distribution of plants. It's changing the way crops grow. Mm-hmm. But yeah, all of these changes arise because of the burning of coal and oil and gas that change the amount of heat absorption in the atmosphere.
If the cycle continues and we continue to burn carbon and carbon dioxide goes into the atmosphere, right, that 50% that is in the atmosphere is not going to change.
Right.
Can you continue to?
Yeah. Eventually it will be removed from the atmosphere, but we're talking like geologic time. So centuries, maybe millennia down the road. Mm-hmm. The CO2 will be taken up by the oceans, will be turned into rocks. But on a human timescale, on like a historical timescale, it's essentially a permanent change to the atmosphere. The atmosphere gets more and more and more CO2. Every time we burn anything made of carbon, we increase the CO2 in the atmosphere permanently, and that raises the temperature permanently.
And that's going to continue happening
until we stop setting carbon on fire.
And the effects of this is a warmer climate. And as you mentioned, what are the main problems that a warmer climate causes on the Earth?
So we already have some problems from this. Probably it depends where you live. Okay. Yep. So one of the things that the warmer climate does is it makes the oceans get deeper. So why do the oceans get deeper? The oceans get deeper because as they warm up, the water actually expands. So warmer water takes up more room. So that will make the oceans deeper. But maybe more importantly, there's quite a lot of water in the world that is on land as ice, particularly like Antarctica and Greenland. There's a huge amount of water in those big ice sheets that are at the poles. And as that ice melts, the water is transferred from the land into the oceans, and that raises the oceans. So sea level rise, we've only had about a foot of, the oceans are a foot higher than they were a couple of 100 years ago. But yeah, by the time, I have to be careful, but by the end of the century, let's just say, maybe another 3 feet of ocean. Wow. Now, that's no big deal if you live in Colorado, like I do, 5,000 feet above sea level. But if you live in New Jersey, you might start noticing that the ocean is higher. It's not that bad on the average. What really gets you is when there's a storm. So if you have a storm and it puts 10-foot waves into the town, and your house is 11 feet above sea level, you're good. But if the ocean comes up 3 feet and you get a 10-foot wave, you're not good anymore. Your house is destroyed by the waves. So that's, if you live near sea level, this is probably the biggest thing that global warming does to you. If you live inland, like I do, it's a different problem. It's not too much water, it's too little water. So a lot of people like me live in areas that are pretty dry, semi-arid. And we can't grow crops, we can't grow street trees, we can't grow lawns without irrigation. We have to have reservoirs that we use to water our stuff. And the hotter it is, the more water you have to take out of that reservoir. The more, even a few degrees, it changes a lot how much water it takes to grow corn or wheat or soy or whatever. So it will be a problem, especially later in the century, for growing food in dry-ish areas. Another thing is wildfire. So as it gets hot, the forests dry out. Fire needs 3 things. It needs fuel. The fuel has to be dry, and then there has to be a spark, some kind of ignition. Well, there's pretty much always been sparks because of lightning, because of, think of like the bad fires in California last winter. Electric lines can make sparks. But as those trees dry out, they are much easier to set on fire, and then the fire can really spread. So floods, droughts, fires, these are sort of the big ones. And then if you think about it, all of the social, economic, political kinds of consequences of those things. So it's a big world. Only 4% of people live in the United States. Let's say that slowly. 96% of people do not live in the United States. And huge numbers of people, billions of people, are very vulnerable to these changes because they don't have the kind of money and the kind of infrastructure, insurance, banking, all the kind of stuff that we take for granted in the U.S. If you live in Bangladesh, if you live in Uganda, you have very little to protect you from these kinds of changes to food or fire or flood. And those people really get harmed, already are getting harmed in a huge way. I mean, if you sort of project it out a few decades, you can imagine, people calculate that somewhere between 500 million and 2 billion people, so give or take 1 billion people, will be displaced from their homes because of sea level rise and because of extreme heat and humidity, especially in like the Middle East. So perhaps you've heard that immigration is kind of a hot topic in the United States these days. What would happen if there was 100 times as many refugees and immigrants around the world? I mean, it would lead to conflict. It would lead to people fighting with each other. And so you can sort of imagine how it starts out small with, it's too hot today, but then it turns out to be floods and droughts and fires. And before you know it, you're talking, social and economic collapse and refugees and war. Wow. So that's kind of the really scary downside.
That is, yeah.
Off the Leash Podcast is brought to you by Skinletics. Now listen, if you've never used light therapy before, you should have started yesterday. But the good thing is there's still lots of time. It is the best thing for you recovery-wise. If you're an athlete and you like working out, it really helps reduce inflammation. And if you're somebody who just cares about their health and well-being, they have a face mask that's really good for anti-aging and anti-acne properties. I'm going to put the link in the description. On top of all of that, they make amazing apparel as I'm sporting right now. Listen, if you watch our podcast, if you're a part of the OTL community, you got to tap into Skinletics. Go ahead, check it out. Hope you enjoy. Let's get back to the episode.
We discussed a lot of the detrimental effects of climate change dating back to how we started, where we are currently, and where we're potentially going. I think it begs the question of what type of things can be done to help mitigate this.
Good question. So kind of a weird inside baseball thing is that the word mitigation in climate policy refers to preventing it. And then we have another word, adaptation, which is what you do to deal with the effects. So probably both fall under what you're asking about, what can you do to mitigate. But at the very least, in the here and now, or today, people are adapting to climate change. And by adapting, I mean, it's stuff like farmers growing different crops, farmers irrigating maybe where they didn't used to have to irrigate. Where I live, and there's a lot more fire danger, we have different building codes and land use codes where you have to leave a buffer of cut down your trees that are up next to your house because they might catch your house on fire, and the firefighters don't want to come in and risk their lives putting out the fire. Building codes, things like in Florida or in Louisiana, they have to build their houses on a high enough foundation that the water doesn't come in and stuff like that. So these are adaptation measures. Adaptation is especially important at the local level. So, when you think of zoning for housing or zoning for office buildings, where's the 100-year floodplain? Are they going to put apartment buildings in there? Are they going to put in maybe a shopping center because they don't want to put people in harm's way? That is mostly a local jurisdiction that deals with adaptation to climate change. On the other hand, mitigation, what we think of as mitigation is reducing emissions, reducing the burning of fossil fuels. So mitigation policy typically involves decarbonizing energy. So almost all of the burning of carbon, more than 75%, is for energy. So there's electricity, but there's also heating fuel and cooking fuel and manufacturing and shipping and airplanes and motor vehicles. All of that stuff is energy. And what do we mean by decarbonizing energy? Well, we can make electricity with solar, with wind, with hydropower, with geothermal power, with nuclear power. All of these are ways that you can make electricity that doesn't involve setting carbon on fire. And then, if you can do that, then you want everything to run on that clean electricity, right? So the sort of cliche version of this is, how do you fix this? Two steps. One, clean up electricity, and two, electrify everything. So you want everything to run on clean electricity. Now, that's not simple. I mean, some things like the lights, sure, no problem. The lights can run on electricity. But what about your car? Yeah, you know, a lot of people have cars that burn gasoline. Over time, they need to be replaced with electric cars that can run on electricity that was generated by solar and wind and geothermal and so forth. What about heating? You know, instead of burning gas in a building, in a furnace, we are looking to do heat pumps where you take heat from the outside and move it to the inside using electricity. It's basically an air conditioner that runs backwards, cools the outside and warms the inside.
Okay.
Yale is building a gigantic one over next to the building where I work. It's a huge construction site, parking lot. They've drilled these big 800-foot deep holes. They're getting heat out of the ground to heat the buildings at Yale.
I don't think I necessarily fully understand this concept.
Think about your refrigerator. Your refrigerator keeps the milk cold. How does it do that? Well, it's like magic, right? You plug it in and it keeps the milk cold.
Yeah, there you go.
But the way that works is that the refrigerator takes heat out of the cold fridge and puts it into the warm room. This is a heat pump. If you care, the way it does this is by boiling a fluid or refrigerant at refrigerator temperature. That's now absorbed the heat from the fridge. You pump it out the back into those coils on the back of your fridge, and then pistons scrunch it down so that it condenses to make a liquid again. And when it condenses, the heat that was put in to boil it comes back out in the kitchen. And that's why the back of your fridge is warm. It's taking heat out of the fridge and putting it into the kitchen. So if you turn that 180 degrees, you take heat out of the outdoors, which makes the outdoors a tiny, tiny bit colder, and you put that heat in a building, and now the building stays warm. So I have one of these things at my house. It's about the size, smaller than this table. It's like maybe the size of a dishwasher. Okay. And it's like a big, powerful fridge that during the wintertime, and I live in Colorado where it's cold in the winter, cold air comes out of this box and goes out into the outdoors, and hot air comes into my house. My house is 100 years old, and I don't have to use any gas to keep warm. I just pump the heat from the outside to the inside and uses electricity, but I got solar panels, so there's no fire. And my house is staying warm through solar-powered electricity that then pumps the heat from the outside.
Wow.
Yeah, and Yale is doing this too.
It's impressive.
It is.
Nice.
So we can do that. We can use electricity for manufacturing. Many, many, many things in the global economy can be run on electricity. And that electricity can be generated with solar, wind, hydro, geothermal, and nukes. The trouble is that they're not always on, right? So like the sun is down every night. What are you going to do at night? You want lights. The wind is not always blowing. But if you take the sun and the wind and the running rivers together, they're less flaky than just the sun, right? There's more consistency if you add these things together. And then nuclear power runs 24/7, so that's good. And geothermal runs 24/7. So you want some combination of these five things. And then you probably have to think about the fact that where in the world is there a lot of sun? The Sahara. How many people live in the Sahara? Not very many, right? So you have to have some way of getting the electricity from where you got it to where you want it. In the U.S., it would be like Arizona has a lot of sunshine, or Nevada, but you want it in New Jersey. You know, so you've got to have power lines that carry it from where you have it to where you want it. Failing that, you have to have batteries that will store it from when you have it to when you want it. So you can either move electricity in space, which is transmission, or you can move it in time, which is storage. And between those different sources and the transmission and the storage, we can pretty much do this.
So you mentioned five. You mentioned nuclear power, geothermal power, solar power, hydropower, and wind power.
Right.
And those are five different ways of
making electricity
rather than using gas.
Yeah. Well, you exactly. And then you have to use that electricity to run the world, right? So it's sort of two separate things. One is that you have to make a lot of clean electricity. And the second is stuff has to run on electricity, right? We currently have a lot of stuff that doesn't run on electricity. A lot of factories use fuel. Airplanes use fuel. My car, I have an electric car too. So
Nice.
yeah. But you see what I mean? There's not just the making the electricity, you also have to use that clean electricity for everything.
So it's like making the electricity, you're referring to like solar panels, for example.
Yeah.
Or the wind.
Wind turbines.
Wind turbines.
Water running over a dam, all those things. Nuclear power.
Okay.
Yeah.
What exactly is nuclear power?
Nuclear power is, believe it or not, so let's return for a second to the old-fashioned thing, the coal-fired power or gas-fired power. Mm-hmm. What is that? That is basically using a fire to boil water, right? So you have a big fire made out of coal, you boil water, you make steam, and you push the steam through a turbine, and it's turning a crank to make electricity. Okay, this is how electricity has been made for hundreds of years. Mm-hmm. Yeah, 100 years. Nuclear power is the same thing, only there's no fire. Nuclear power uses radioactive rocks, and if you make a big enough pile of radioactive rocks, it gets really hot in there, and they pump water in pipes through the pile of hot rocks, and it makes it boil, and then it makes steam, and it turns a crank. So it's really the same underlying technology as turning a crank. I mean, wind power turns a crank, water power turns a crank, gas, coal, oil, they all turn cranks. Mm-hmm. Nuclear power is just a fancy way to turn the crank.
Now, the next question I have now is how do you take these energy sources and now apply them? You mentioned, for example, it's really hot in Arizona. So you want this solar energy to get to New Jersey. How does that happen?
Yeah. Great question. So it's hard. I mean, simplistically, you might think, well, we just got to use the grid. We have to have power lines. And we have power lines. But it turns out that the power lines we have, they use a kind of electricity called alternating current, AC. Maybe you've heard of that. The direction of the electricity switches directions every 60 times a second. Like just a plug in the wall. It's just like switching the positive and negative 60 times a second. You do that in a big power line, and it makes magnetic fields. It makes the power line into a magnet, and that magnet actually pushes back on the power, pushes back on the electricity. And so, if you try to push electricity from Arizona to New Jersey, it's not going to get there. It's going to make a monster electromagnet out of that wire, and you can't push the juice through the magnet. Mm-hmm. So, to get electricity thousands of miles like that instead of hundreds of miles, you need a new kind of transmission line called high voltage direct current. Direct current doesn't switch directions. It's just, one way through the wire, and they're big, like 4-inch diameter copper cables, and they can transmit electricity for thousands of miles with almost no loss. We have a few of those in the United States, but where they really have a lot of them is China. China is building out these huge amounts of solar and wind. A lot of their solar and wind and also hydropower is in the west part of China. Just like we have deserts and mountains in the west, China has deserts and mountains in the west. So think like the Tibetan Plateau. They're building all these power plants there, but their industry and their population is mostly on the coast. So they run HVDC lines all the way across. They have tens of thousands of miles of HVDC lines in China, and they move their electricity from one end of the country to the other to keep the lights on.
Interesting. I'm curious of what's stopping us from doing that.
So that's a good question. 10, 20 years ago, what was stopping us was that it was expensive. So let's say year 2000, maybe even worse, like 1980. I don't know if you must have ridden in electric cars.
Yeah.
Yeah. So like think of a Tesla. Has a great big battery in there, right? Because drives 300 miles or 350 miles on a charge. That battery in 1980 would have cost millions of dollars. There is no way anybody was going to make a Tesla in 1980 because nobody was going to pay millions and millions of dollars for a car. The batteries are 1,000 times cheaper than they were in 1980. 1,000 times cheaper.
What caused them to get cheaper?
Essentially, people learned better manufacturing by practice.
Okay.
We call it economies of scale, right? In 1980, these kind of technologies like solar panels too, they would have been like a prototype built in a lab that guys in white coats are like tinkering with these chemistries and stuff. As people build more and more and more of these things, we learn. We learn by doing. We learn how to build better factories to build better solar panels, and we as we crank out twice as many solar panels, they get 50% cheaper. I'm making these numbers up,
sure.
But the price of these clean energy technologies has just plummeted, especially the last 10, 15 years. So now that is no longer the reason, right? I would say it used to be that it was cheaper to burn coal and gas than it was to make electricity from wind and solar, but that is no longer the case. Now it is actually cheaper to use wind and solar than it is to use coal and gas. Instead, if you think about, we're asking a lot I'm asking a lot. Oh, why don't we just shut down, trillions of dollars worth of infrastructure and build a whole bunch of new solar and wind and power grids and batteries and stuff. I mean, it's a lot of work. It's comparable amount of effort to big infrastructure changes we did 100 years ago. I like to think about my grandparents' generation, not them personally, but their generation retrofitted all the world's cities with indoor plumbing. Let's just think about that for a minute. Imagine you had to call up plumbers on a phone and say, okay, I would like you to knock out all the walls in every building in Manhattan and put in hot and cold running water all the way up and down those buildings. And then I want some drywall contractors to come in and knock out all the interior walls in every apartment in New York and put in toilets and sinks and showers and then put the drywall back. Like, what do you think that would cost? Oh my God.
Yeah.
It's just staggering.
Yeah.
And unbelievable, but my grandparents' generation actually did that, right? And they didn't just do it in New York. They did it in London and Paris and Tokyo. I mean, the whole world. It was this incredible amount of money. Now, where did that money come from? How did they afford this ginormous project? They had to dig up all the streets and lay sewer pipes. I mean, it went on and on and on for years. Well, they did it by selling toilets and sinks and showers. They did it by, charging people more for their water bill because they had access to all this indoor plumbing. So I think it'll be like that. It'll be a transition. We won't buy a clean power system because we care deeply about the environment. We will buy clean power because we want to keep the lights on. We will buy clean power because we want to drive our cars. And so this is where the money will come from. It'll come from buying that stuff.
I want to talk about water a little bit.
Yeah.
You talked a lot about water with these cleaner energy sources. Is water a big factor in a lot of these, and like in the electricity regarding all 5 of these power sources?
Yeah, let's think about that for a minute. So obviously, hydroelectric power, you got to have water.
Yep.
And you don't just have to have water for hydropower, you have to have a hill. So the water has to run downhill to turn the crank. That's actually fairly rare in the world, right? There's a lot of flat land and there's a lot of dry land. And you're not going to do hydropower if it's either flat or dry or both. For wind and solar, not so much. You don't really need water to do that. You might, I'm sure you need water to manufacture those things, but not as much water as you would for like a big coal-fired, gas-fired power plant that you're boiling water all the time. For nuclear, you have to have water because you have to boil water. So there's water involved. But I think for most of these things, we already use a lot of water for our power. And I don't believe that switching from boiling water with coal to boiling water with nuclear power, it's not 10 times more water.
Sure.
Yeah.
What are the downsides? I mean, of switching to cleaner energy sources?
Yeah.
Other than, I mean, you mentioned the severe amount of work, money, resources it would take. But when it comes to actually, let's say we fast forward however many years and we have cleaner energy running, hopefully, portions of the world. What are the downsides?
Well, the downside is huge if your income all comes from selling coal, oil, and gas.
Yeah.
So people whose business it is to sell the coal, oil, and gas, they think this is a terrible idea, right? They want it to stop. They want to go back to the way things used to be. Some people will respond to this by saying, well, it's gonna require mining of a lot of materials, which it will, right? I mean, building a bazillion windmills, you're going to have a lot of steel and a lot of concrete and a lot of aluminum. So you're going to have to go mine those things. Electric batteries, batteries for electric cars, you got lithium and you got, various metals and stuff in the batteries. So these are environmental costs. There are downsides, but they are so much less mining than we are currently doing for coal, oil, and gas, right? So probably the total amount of mining in this transition is 95% less mining than we do now.
Oh, wow.
Because we dig an unbelievable amount of coal, oil, and gas out of the ground every year to keep everything running. And we wouldn't have to do that if we had the clean energy economy. What other downsides? It will change geopolitics. Countries like Saudi Arabia or Russia or the United States. I mean, the United States is the biggest producer of oil and gas in the world.
Really?
Yeah, isn't that wild?
I didn't know that.
When I was a kid, we were not. But we because of fracking, we learned how to get a lot of gas out of the rocks. And we now make more gas than anyone else. So some people in the United States that make a lot of money off of that, they do not want to see a transition away from their industry. They want their industry to stay on top. So, I mean, that's kind of big.
Yeah. I actually wrote down when you were talking earlier, why do we like gas so much was a question I wrote down. And you seem like you just answered in many different ways. Like the geopolitical nature of the world right now kind of run by these big oil industries, and the money involved in oil is something that a lot of people are relying on and have made great careers out of.
It's not that many people. It's a lot of money.
Okay.
So I have a student in my climate change class from Ghana, and I pretty much told the same story to my class that I just told to you. And this guy said, Ghana discovered oil about 10 years ago offshore, and they want to mine it. They want to get the oil out of the ground, sell it for money. They want to get rich. And I don't blame him. And he's got a point. He's sort of looking at me like, you guys pumped a lot of oil. You got really rich. Now we've got oil, and you're trying to tell me I shouldn't pump that oil and get rich like you did. Well, that's not fair. But if you think about it, how many people in Ghana you think are really going to get rich off of that oil?
Not many.
It's probably like 10, right? It's the people that own the capital that can invest it in the equipment, that can go get that oil, that are going to sell it for a profit. And, Ghana might get prestige because they've got more billionaires now. But it's not like we all own an oil well, right? Do you own an oil well?
I do not.
I don't either. So I think this is kind of a good of the few thing. Yeah, there's people at the top of our economy, oil company executives. Oh yeah, they're rich. How many rich oil company executives are there really compared to the rest of us? Not that many.
So that transition is something that I think is a lot of people, well, not a lot of people, very few people, but very important, powerful people.
There's your problem right there. So I I think, and this is my opinion, right? This is not like science. This is my opinion as a smart guy who reads the paper, reads the web. I think that very rich and powerful people do not want this to happen. And they are spending a lot of money on lobbying and on political activity to prevent this kind of transition from happening, particularly in, you might call us petrostates, countries like Saudi Arabia, like Russia, like Venezuela, the U.S., that have a tremendous amount of money coming in from oil and gas. On the other end of the spectrum, there's billions of people who are not making money off of oil and gas. And those people stand to benefit from transitioning off of oil and gas and onto solar and wind. And it's hard for us in the United States or Europe to give up on an energy system that works pretty good to build a brand new one that'll be better. But if you were doing this in Africa, you would not be starting from a really nice, big energy system that works great. You would be starting from scratch. And if we were to start from scratch here, like we did 150 years ago, we would not build a fossil fuel system in the United States today because it's more expensive than the solar and wind and transmission kind of system that we could build. So my expectation is that as the developing world develops, as they build out energy for their people, they will be building the less expensive, not fossil energy systems. And it's the rich countries who will have the most resistance to this because we already have existing infrastructure that works pretty well.
Question for you is there any rich country, you mentioned China a bit earlier, that has taken initiative and is starting to do things pretty well?
Yeah, for sure. So several countries happen to have fantastic low carbon resources, like Iceland, right? Iceland is sitting on a freaking volcano. So their energy is essentially free. They use hot water for everything. They make all their electricity from hot water. They heat all their buildings from hot water. They do manufacturing from the electricity from hot water. It's like almost a zero carbon economy now. Uruguay, it's a small country in South America, mostly wind power. It sticks way down into the South Atlantic. It's really windy. They just run the whole country on wind. Norway pretty much runs on hydropower because they have these giant mountains that run down to the sea. China is the big example of they are the biggest burner of fossil fuels in the world. They emit twice as much CO2 as the United States, much less per person, but they have a lot more people. But in the last 15 years, they have just gone absolutely bonkers for clean energy. They each year deploy twice as much solar and wind as the rest of the world put together. So it's amazing. I think in 2024, China built more solar in 2024 than the United States has built in our entire history. So it's amazing. They are just going full throttle towards developing clean energy. They've got the batteries, they've got the electric cars, they've got the electric trains. It's like they've decided this is the strategic move. And unlike here, if you complain to the government too much, they put you in jail or shoot you. So they can get away with doing things at a different scale or a different speed than here. You'd have to convince people and people would have to vote for it, right? But authoritarian countries, they pretty much do what they want. So yeah, there's a number of examples of countries that have made this transition already.
I think a good transition for us now would be talking about how individual human beings can live cleaner.
Yeah.
As we've talked, you've already mentioned yourself and your life, and you've mentioned 3 things that I caught is the electric car. You also mentioned the way you heat your house.
Yep.
Is something I learned today for the
Electric
first time.
heat pump.
Electric heat pump. I feel like you mentioned something else.
Solar panels.
Solar panels on your house.
Yeah. Well, they're not on my house because I have trees. But I bought into a thing. Our city runs a community solar facility where you buy the panels and the city hosts them on racks. And so I don't have to have them on my house. The city just runs it for me.
And then they
But
power to your house, power line.
no, it's not like that. It just goes into the grid and they take it off my bill. So my panels are generating electricity, and they just subtract it from my electric bill every month. But wait a second, these are rich people things, right? so electric car, solar panels, heat pump. These are all thousands and thousands of dollars for each of those things. Mm-hmm. What can you do if you don't have $30,000 to burn on this stuff? There's all the little things that I'm going to say your mom probably told you to do, right? Turn off the light when you leave a room. Mm-hmm. Use the light bulbs that don't, the old-fashioned light bulbs that made heat. We don't use those anymore. Take the bus or ride your bike to work, things like that. But these are pretty small potatoes. You can vote. You can talk to people and try to. You could do podcasts. You could try to sort of build sort of a groundswell of support for these ideas through communication. But different people have different interests, different skills. So at the end of my class, end of my semester, I always draw a Venn diagram. You know what those are? With the circles, right? On the chalkboard, whiteboard. Mm-hmm. First circle is what are you good at? What are you good at? Mm-hmm. Well, you play football and you do podcasts. I don't know you well enough to say anything else, but you're obviously pretty good at both of those things. The second circle is what do you really love to do? And, sometimes we have things that we're good at, but we don't really like. And sometimes we have things that we really like, but we're not that good at. But if you find the overlap of those things, the things that you're good at and you love, and then there's a third circle. And a third circle is stuff that will help the world, stuff that will help the world be a better place. Mm-hmm. And what you want to do in your life is to find the overlap of those 3 circles. And when you do that, oh man, you have tapped into your purpose. Mm-hmm. This is your superpower. Mm-hmm. So for some people, it's going to be engineering, and they're going to invent the next level of solar panels or batteries or something. Fine, but there's not that many people that do that. For some people, it's going to be communication and journalism, which is kind of where you're headed. Mm-hmm. Wonderful. You can make so much more of a difference by being a powerful communicator and journalist than you can by riding your bike to work. Mm-hmm. You're leveraging your superpower to move the needle in a way that you can't just in your own life. For some people, who knows? Maybe they're accountants. Mm-hmm. Well, then you could go be an accountant for some, battery company or accountant for a solar panel company. Maybe you want to be a rock and roll star. Mm-hmm. Well, go sing songs about climate change. I don't know, but whatever your thing, right? Find your special niche in this world of stuff that can make the world better, and do that. You do your special thing. Mm-hmm. Now, that sounds really good. Let me tell you that I did not make that up. Mm-hmm. This is from a wonderful climate communicator named Ayanna Elizabeth Johnson. And you can find her TED Talk about the Venn diagram. And she's awesome.
In your opinion, do you think the world, or maybe let's start more granular, the United States, is interested enough in long term to try to, I don't necessarily understand enough what net zero means. I think it just means like you're even.
Yeah. What most people mean by this is that you reduce your emissions to the point that growing forests, oceans that are dissolving CO2 take up the rest so that you don't have any, the CO2 stops increasing. That's what it means.
So the question I'll have is, do you think there's enough buy-in in the geopolitical landscape to eventually achieve net zero?
Yes, I do. I really do. It would be good to do it pretty quick because things are moving fast. Scientists say we probably have to get to net zero by like 2060.
Why is that the year?
Well, why is that the year? The countries of the world have negotiated and said we want to hold global warming no more than 2 degrees Celsius above pre-industrial levels. This is legalese. This is, comes out of an international treaty. You just do the math and you say, if you don't stop burning by about the middle of the century, you're going to blow through that limit and violate the international treaty. That's why it's that year. But it's probably better to say every 1/10 of a degree matters. And, if we go to 2 degrees, that's worse than 1.9. And if we go to 2.1, that's worse than 2.0. And so wherever we go, we got to get to net zero. We do. It would be, I would like to think it is inevitable, but it's not. It depends on the choices people make. So we need people like yourself who are in journalism, in podcasting, to help people understand this. The U.S. has 4% of the world's population, and we make about 15% of the world's CO2 emissions. So per person, we emit 4 times what the average person does. But 4% of the population is not that much. So China emits way more than the U.S., and they're moving fast. They're gonna start shrinking their emissions pretty quick. Our emissions have been going down for 20 years in the United States. We have 20 years of progress, but we're not anywhere near zero. Europe is a big emitter. Europe has been reducing their emissions for 50 years. European emissions peaked in the 1970s. So, I wouldn't say it's all down to the U.S. I think there's a U.S., Europe, China, India. Then you get into like second tier, like Indonesia and Brazil.
Yeah. I tell myself that my target audience for my podcast is young adults, people in college, people similar to my age, going through their 20s, and the newer generation. And it seems that the newer generation, and the conversations I have, and also myself prior to the episode, have a pretty low understanding of kind of what's going on in the climate arena, we could call it. But the question I have to you is, what exactly do you think the average person should know and or understand about this arena to hopefully make well-informed decisions day to day?
Here's a really quick little list of bullet points that you should know.
Nice.
Adding heat to the world warms it up. Burning carbon traps the heat, so burning carbon will warm up the world. It's permanent. So we're going to have to stop. I mean, that's basically it. The every time you burn fuel, you are turning up the thermostat of the world, and it's not going to go back down. The day will come when you say, that's hot enough. I don't want it to go any hotter. And by that time, you have to have something else to do besides burning carbon. So get on it. I mean, that's what people need to know, is that it's there's kind of no wiggle room around that.
I think I want to finish up by touching on, got a chance to read a bit about you. It seems like you had a very cool career. You've done a lot of research. I would love for you to tell me maybe the favorite experience you've had throughout your research, maybe the coolest memory or something that you really enjoyed.
Okay. I spent many years trying to understand how carbon is taken up by the trees in the Amazon rainforest. And in 2001, I worked with a guy in Canada named Ray Desjardins. He built this instrument, and we shipped it to Brazil, to the middle of nowhere in the Amazon. And I flew down there, and it was hot. Like, I don't know if you've ever been to like Florida in July.
Yeah.
It's worse than that.
Oh
and it's always like that. Super humid, super hot. And it was smoky.
Mm-hmm.
And I put this thing in the back of a little airplane, like not a fancy research plane, but like the kind of plane that you hire to fly you to some other town.
Mm-hmm.
Little 4-seater. And machine is like seat belted in the back seat. And I'm sitting in there with the pilot, and I wanted him to fly a certain pattern, and I was going to measure the CO2 all over the place and figure out how much the trees are taking up. And a little tiny dirt airstrip in the middle of nowhere in the jungle. And before we got in the plane, the pilot crossed himself. He didn't speak much English, Portuguese. I don't speak that much Portuguese. Guy crosses himself. I'm thinking, oh my God, what have I done? I get in this little airplane. We fly off over the jungle. Yeah. It's incredible. Just, I mean, you can see forever, and it's just this forest that goes on for thousands of miles. Every tree is different. It's an amazing place. We flew over the Amazon River, and the Amazon River is 20 miles across, so you can't see the other side. I mean, it's like the ocean. Mm-hmm. And then we flew back, and we sort of did this big spiral to try to do a vertical profile of CO2 concentration. And then the atmosphere mixes like with turbulent eddies, and we popped out over the top of the mixing layer, and all of a sudden, it was cooler, it was less humid, and I was just like this. And this is like one of my favorite memories of this airplane flight in, the remote jungle in the Amazon and taking measurements of the CO2.
Would you say that's probably the coolest place you've ever been?
Yeah, I've been to some cool places, but that was a wonderful work moment. That was the month before 9/11. I came back, and the world kind of went bad the next month. Mm-hmm. Yeah, that was fun.
That's awesome. What do you hope for? You've reached this. You're teaching now. What do you hope the rest of your career looks like? And what are your goals? Maybe.
I love the teaching. This is my third semester visiting at Yale. I love teaching here. I understand that there are some significant money problems here, and I may not be able to come back because they have to protect people whose real careers are here, and I'm just a visitor. I am teaching every 3 years on a ship. Starting on January 5th, I have a gig with 500 undergrads on a ship from Thailand. And I'm going to take them around the global south, learning about climate change and economic development. So we go to Thailand, Vietnam, Malaysia, India, Kenya, South Africa, Ghana, Morocco, and then we finish up in Europe. And so that's super fun.
It's fascinating.
Yeah. My wife goes with me, and we go to see all these countries and take students. I have a cabin on a mountaintop in Wyoming where I do astronomy, photography of distant galaxies. So I have hobbies.
Distant galaxies?
I do.
Really?
And I have a Labrador retriever that I throw a ball for. This is my career now. I'm an old man.
This sounds like lots of fun.
Yeah, it's great.
Sounds like you're enjoying it.
I love it.
Awesome. Well, I really appreciate you doing this episode with me.
You bet.
I learned a ton.
Great.
And I hope everyone listening learned a ton. So subscribe to Off the Leash Podcast, and we'll see you next time.
All right.